Hi everyone, I'm Mohamad. I work at HPE. So today I'll just give a very brief overview of what we have in the latest 264 release in terms of the client-side changes, especially on the POSIX side. And we'll talk about some work we're doing on client-side caching. And most of the credit will go to my coworker, Lei, who also works at HPE. Quick updates on just container settings. I think John might have mentioned some of this in his talk, but I'm not sure. I'm giving the DAOS tutorial at the same time, so I had to skip that part. But we added RF3 support for containers. So we have RF3 support from before, but we didn't have erasure coding settings for RF3 for files and objects. So we added that. So we have 3 parity EC, for example, 16p3, 8p3, and so on. So that's actually now what we want to recommend users to use, especially on a large system like Aurora, for example. And we're making that sort of the default setting. So before, if you're using 263, if you set RF3 on a container, you would get RP4, for example. But today, for files, with 264, you'll get an EC object class. So that's good. So one thing also we have is that, the redundancy factor. We know it's been there before, the redundancy factor of a container inherits the pool redundancy factor. You can set this property artifact 3 on the pool, and the container will inherit it. So you can do that to have all users so who are creating containers inherit the artifact, the redundancy factor if they don't set it. However, one thing to note, this is not like containers enforcing redundancy factor for objects. It's not restrictive in the sense that users can override this with a lower setting, right? So if you can set the redundancy factor for 3 at the pool level, but users can create still RF0 containers if they explicitly set that. So that's just one thing to keep in mind. In the future, we want to have more. This is going to be an ongoing effort, but better defaults. Make redundancy factor 2 or 3 the default in everywhere whenever users are creating. So today for automatic object class selection, just a summary of what you get when you set the redundancy factor. For 0, you get SX for file, S1 for directory. For RF1, you get a 1 parity GX for file, to a replication G1 for directory, and so on. So I think just the last column here was what's new in 264. So another new thing that's in 264 is the chunk size selections for DFS. So by default, automatically DFS used to set 1 megabyte chunk size regardless of what your settings are. So that creates problems sometimes, because if DFS uses 1 megabyte or you set the chunk size to 1 megabyte, you can sometimes have, and your application is doing large I/O. Sometimes you can create partial stripe updates all the time. So, and you get bad performance, and you can cause the system to slowness in the system if you are going to keep aggregation happening on the server. So today we sort of set this automatically now. So we take the EC cell size of the container, we multiply that by the data shard, and actually increase that also double to set automatically DFS chunk size. Again, this can be overridden by the user when creating the container, but if they don't set it, we automatically set it today. And yeah, one thing, since RF3 was newly added, we missed adding that optimization for RF3 containers. It will be in the next release. So another thing we added for 264 is having a way to launch diffuse in a scalable manner on big systems like Aurora, for example. We found out if you are mounting diffuse from every node, and you have 8,000, 10,000 nodes mounting diffuse at the same time, that was pretty slow. It was taking sometimes 10, 20 minutes out of the job to just mount diffuse. So that was a pretty hard pain point for users. So we have a new way into 6.4 to use the local to global, global to local, maybe like similar like to a collective open to a collective mount. Basically, we have one user, one node mount diffuse, and dump the handles into a temp file, and you can have other mounters read the temp file and mount diffuse themselves in that case. So the main use case is just large jobs on big clusters that trying to mount the same container. There's of course a caveat here that there's a root mounter. That first person that mounts is the root mounter. If they unmount, everybody loses their mount. So that's a big caveat here. That's sort of the collective way of doing things. So it works for most scenarios, but for some other scenarios where things are independent, this is probably not the way to go. Any questions before I move on to the next topic? Okay. So let's go into this new thing with client-side caching. This is, I think you've seen the slide a lot, of how our POSIX architecture is. libDFS at the bottom, then we have diffuse with interception, and the main thing so far is that today, if for most cases, using diffuse plus interception works great. The main issue there is that client-side caching you don't get client-side caching if you're not using Fuse directly without interception, right? Fuse has you can mount diffuse with caching enabled, enable write-back caching, read ahead, and things like that. But the diffuse itself is slow, so to get the best of both worlds, sort of, we need something like. So we need something at the DFS layer to do some caching optionally, right? Pill for DFS, this interception library has some caching, but it's very limited, just for lookups, for example. And it's also the scope is limited to a single process address space. So even if you have multiple processes running on the same node, each have their own cache in DRAM, so it won't benefit from that. So as I said, diffuse does some caching itself, and it's actually beneficial in some cases to use diffuse without interception and go through the performance hit in some cases, right? But not in all cases. If you do I/O, it's better to go through to interception. So sort of we want to have something like to get best of all worlds. So if we add DFS caching, similar to what diffuse does, allow to turn it on or off, that could get us the best of both worlds and bypass diffuse entirely for all use cases. So we've seen those use cases be useful in things like sometimes in these training workloads where there's an initial scan done by all processes, even on the same node, right? That creates a long startup time when using DAOS, because everybody is doing scanning of the tree, lookup, file stats, and things like that. There are other cases where you're even on multiple nodes. You can have like some use cases where you can have write once, read many scenario. You just import your data set and everything is a read only scenario. So that's sort of another use case that you have if you have multiple threads, multiple processes on that node. So the way we're taking this is, starting small, just handle read-only use cases first, and then expand later to have, sometimes read-write with a read-ahead, write-back, and it's going to be limited to a single node. We're not doing distributed client-side caching here. The work is done in a feature branch and on GitHub. And there's no release target for it yet. It's no POR or anything like that. So it's just still exploratory work at this point. So the idea here is to add a DN3 cache at the DFS level, a reader cache and a data cache, read data cache here. And in the future, maybe we can move that a level down do it at the KV level and enumeration level. And why? Well, you say, yeah, you can ask why we don't start there from the start. That libDAOS is way more complicated. So to get just something quick, and just to test it out for different use cases, doing it at DFS level is much easier. And as you'll see, the utilities we are working with can be shared across different layers in the future if we want to. So what utilities do we need that we are working on and to implement this? So DFS, to add something in DFS, since it's in user space, there's no IO agent that's collecting the IO, like Fuse, for example. There's an IO kernel, everything. There's a cache that can be managed there. So there's no shared address space just within DRAM, just in DRAM, right? We need to use shared memory to have multiple processes with different address space to implement such caching on the client side. So the first thing we need is a shared memory allocator, right? Has an initial implementation that's based on TLSF. I forgot what that stands for. Sorry about that. But yeah, we rely on that. The idea is to have the DAOS agent maybe first create the shared memory region when it started, and it destroys it when the agent exits. Today, the implementation actually has the first process accessing this created and it's later destroyed. So, but that implementation will change. Initial size of that cache will be fixed, but we can work on improving that and having it to be able to extend it and later. The second thing we need is a shared memory mutex and read-write lock. So we need a robust mutex, of course, because processes can go away or crash anytime without releasing the lock. So that has to be properly implemented. And the implementation is based on pthread implementation with looking at a robust mutex, and it has also added read-write lock support, which performance looks okay, but it probably needs some work handling some hard edge cases. We might try to improve it a bit to maybe penalize the edge cases more and to allow a faster implementation, but that's still a work in progress. And finally, we need basically a hash table and LRU in shared memory using the shared memory allocator to be able to store the entries and store buckets for the read cache and put data caching there. So as I said, the idea, the initial implementation today has processes creating. The first process creates a shared memory region, and others try to create it, and if not, open it. But we want to move that to the agent eventually. And everything today requires read-only access on the container because we don't support, conflicting updates just some other people outside of the node, like changing the going behind us on the cache. So the container has to be mounted read-only to be able to use that. And the second step will work on supporting some limited read-write cases in the future. So today we have a de-entry cache. It's a simple LRU policy. We have a way to serialize, for example, the DFS object, the file or the directory, and store it in the cache and retrieve it when we need it. And so we also cache file sizes when they're looked up, if there's a lookup plus stat, because we know querying the file size on DAOS can be very expensive. So that's very important to keep track of the file size, just in case it's repeatedly statted. Reader cache is in the works, trying to create basically a bucket. We have a new API because the anchor that we use is complicated with DAOS, so we had to build a new anchor at the DFS level to be able to track the ID and the bucket offset in the cache. The idea is to store buckets of reader items there instead of as you are reading, once you cross the next bucket, you read it, you pull it into the cache, and so on. And lastly, what Lay is currently working on is the data cache, something like read ahead or pre-read small files, or the first chunk of the file on open, for example. And this can sort of be done asynchronously when you open the file, and this should improve some read performance. As I said, this is still really in the works. There were some initial performance results that I'm not going to share here because they're not very interesting. They just show that, so far, as we use this, if you're just comparing doing everything in DRAM versus shared memory, sort of the result is almost similar. But we're trying to get more tangible use cases and test that with as we are working on the implementation. So I think I'm out of time, so that's all. Thanks.
Thank you. Questions from Mohamad?
So is the intention here to disable caching and fuse?
Yeah, totally bypass fuse.
And how to share, not to totally get rid of fuse.
Yeah, so we're not getting rid of fuse, but just keep limiting what fuse is used for, right?
But fuse can use that. So now,
Yeah, that's what I'm saying.
so fuse and intention memory will use the same shared memory region. So that
Right. I mean, if you what we are testing.
everything is in channel.
What we are testing mostly is with interception, right? But technically, if you mount defuse with disabled caching, but you enable caching in DFS, we can get something similar. Right?
And they should be all consistent.
Yeah.
Assume there's some issues with multi-user defuse in that case.
So multi-user has different issues also because how the shared memory region is accessible today, because it depends how you create it. If it's from the agent, how you manage access versus each process creating its shared memory region. So that can be a little challenging to support.
If I wanted to see some metrics around caches, hit rates, or whatever, is there a way to do that?
Since the implementation is ongoing, there's no way to do that today. But yeah, it's definitely something we want to keep track of.
Yeah, I'm not sure what the best way to expose those would be.
Yeah, so we actually have that's aside from this talk, but the DAOS agent, you can export metrics through the DAOS agent it actually uses shared memory to dump those metrics, but there's also can be imported into, what's the tool called? Prometheus, yeah.
Any other questions?
For the shared memory, are you guys also looking at just using huge page back memory, or just simply shared memory? Any investigation on the page side?
Today we're just using the POSIX shared memory create and that. So, but yeah, I mean, what we do underneath is open, right? We can try anything.
If you ever try to RDMA register,
No, yeah.
then you'll want to.
Yeah, sure. I mean.
All right, thank you, Mohamad.
All right. Thanks.